Well, I'd like to share with you today a status report on the LADEE mission, which is one of the two upcoming lunar missions, GRAIL being the next one, and Maria Zuber will tell you about that later in the morning. LADEE is focused on two really important science questions that are left over from the Apollo era, namely the nature of the lunar exosphere. It's a nearby example, the lunar exosphere is a nearby example of surface boundary exospheres found throughout the solar system. And so it makes sense to go to the moon in order to explore not just the moon's exosphere, but also what we would find elsewhere in the solar system. Then there's this question of dust. There's anecdotal evidence and indeed measurements that dust is actually electrostatically lofted off the surface of the moon near the terminator. But what is the nature of the physics of that process, and does it actually really truly occur? And so LADEE is addressing those questions as well. And in 2008, the LADEE mission was commissioned to begin to answer those questions. There's a lot of scientific background for doing this, and multiple, multiple roadmaps and surveys have advocated going after some of these questions at the moon. And in particular, most recently and gratifyingly to me was to see that the NRC Decadal Survey recommended the execution of the LADEE mission, the GRAIL mission, and so forth. Fly these missions out and answer the science questions that they're intended to answer. So, as I was saying earlier, the moon is just one example of surface boundary exospheres found throughout the solar system, and that's why going to the moon will inform us about bodies such as the Kuiper Belt objects, the outer planets, icy moons, and even provide a nice contrast to Mercury. In addition, there's this question of lofted dust and whether it's an explanation for the kinds of things we see on asteroids where you see pooling of dust and so forth. But more particularly, this would constitute possibly a hazard at the moon, and so for future exploration, it's important to know what's taking place with the dust. We already know that there's an exosphere at the moon. Some of it's been measured. On Apollo, Argon-40 was measured. This comes out of the lunar interior. It's a radioactive, it's a radiogenic daughter product from the potassium-40. There's also potassium and sodium exospheres that have been measured for years. These are telescopic ground-based observations. But now we're seeing, in fact, we'll see at this conference, additional evidence that there are other metals and possibly, metals in an astrophysics sense, seen in data from, for instance, L-Cross. So I would direct your attention to Wooden's talk later in this meeting. She'll tell you all about what we saw on L-Cross. And as concerns this dust, this is, again, some of the evidence I was talking about earlier, this lofted dust. This is a horizon glow as seen by Surveyor back in 1968. After the sun had gone down, there was this horizon glow, and it evolved slowly with time as the sun set beyond the local horizon. From orbit, the Apollo astronauts could see extended filaments illuminating well above the horizon of the moon as seen from orbit. This looks like it only is limited to an area just a few meters above the surface, but in order to see this from orbit, material really has to be at very, very high altitudes. And so the suggestion is here that in fact, very small grains of dust may be capable of being lofted to very high altitudes. And that, again, that's what LADEE is meant to address. Very recently, Alan Stern kindly provided me with some information about something that LAMP has been looking for. LAMP is an ultraviolet spectrometer aboard LRO, and they recently have tried to make measurements of a horizon glow above the limb. They had to carefully do this, and then if you have any questions about how they accomplished this on LRO, then you ought to direct your questions to Alan, and maybe he'll talk about it in his talk later on. But basically, they found this evidence for this very low altitude this extended source of illumination or photons in the 160 to 190 nanometer wavelength range. And the question is whether or not this could be lofted, scattered atmospheric dust. The grain sizes would be of the order of 1/10 of a micron or so in size. However, there are strong caveats that the team has impressed upon me, that there is a question of scattered light from the illuminated limb of the moon. So this is still tantalizing, but not confirmed. So let's move on to what's going on with LADEE right now. I'm showing you some hardware from LADEE. These are the payload instruments. The neutral mass spectrometer is being built at Goddard. The ultraviolet and visible spectrometer is being built here at Ames. Tony Colbreit is the PI. Paul Mahaffey is PI on the NMS. This is an engineering unit that has been assembled and delivered. Here is the lunar dust experiment from University of Colorado. Mihai Harani is the PI for this instrument. This is the engineering unit for this. This has been tested at two dust accelerator facilities, one in Heidelberg and another new one at the University of Colorado. Finally, there's a fourth instrument that is not a science instrument, it's a technology demonstration. There's a lunar laser communications demo. It's basically a very, very high bandwidth. It's meant to go up to 600 megabits per second downlink, so to provide very, very high bandwidth downlink for data from the moon and from other planets as well. So if this works, it really opens a whole new chapter in getting data down from planetary missions. Further to the hardware, this is an exploded view of LADEE, and it's going from the top radiator assembly on down to the propulsion module. Here I'm going to show you some hardware that's already here at Ames being assembled. Part of the propulsion system. This is the propulsion deck, and this OCS is the orbit control system. Thruster bracket. This is the big engine mounted. The big engine is mounted to this thing. This is the reaction control system thruster bracket. These are these guys down here. Systems comes from Loral. More hardware, showing you just various things to give you the sense that this mission is really a reality. We're in a fabrication phase right now. We've passed CDR, as you'll see in a second, and we're well into this business of fabricating the hardware. This is a cable harness mock-up so that you can route cable harnesses, and all these other things are templates and jigs for assembling other pieces of hardware for the spacecraft structure. Here's another way you know it's real. We've got a transport container for the spacecraft. So this was flown in by the Air Force, and so the spacecraft will go into losing the laser here. The spacecraft will go into this container for shipping to Wallops. LADEE flies aboard a Minotaur 5. In fact, it'll fly aboard the first Minotaur 5. Minotaur 5 is a peacekeeper, three-stage intercontinental ballistic missile that's been refurbished by Orbital, and there are an additional two solid rocket stages on top of those three. It's a Star 48 and a Star 37, and then LADEE rides on top of that with its own propulsion system. This will be the first flight of the Minotaur 5. There have been several Minotaur 4 flights so far, and they've all been successful. So we have a great deal of confidence in this launch system. It's a very low-cost launch system. Again, opening pathways for flight. This gives you a little history of where LADEE has been and where we are now. As I said, this began in 2008 with a pre-phase A. We've received several positive key decision point decisions at headquarters, and we had mission CDR back in May. The next big milestone is a system integration review. This is in September coming up. That'll be followed by a key decision point D at headquarters on my birthday in 2011, which would be, I know what birthday present I want out of headquarters. And then there will be, of course, a number of other milestones between that and launch, but I didn't want to clutter this up too much. But launch is currently slated for May of 2013, so just under 2 years away from now. And LADEE's a mission of firsts. There's a lot of things that are being done for the very first time on this mission, hopefully to open doors for low-cost planetary exploration, to accomplish significant science with a limited payload and with a small mission architecture. It's the first mission to make use of the Ames Common Bus architecture, which is this composite structure. It's the first flight of the Minotaur 5, which is this modified peacekeeper. It's, which again, as I mentioned earlier, is a cheaper way of getting into space, near-Earth space. It'll be the first deep space launch out of the Wallops Flight Facility in Virginia. They've flown a lot of orbital systems out of there, but none to deep space, like going to the moon. And also, this will be the first opportunity to really test laser communications technology. The laser system could open the door for very high bandwidth downlink from planetary. And there are the aliens again. They really don't want to see this go. Okay. Anyway, that's it. Thanks very much.
Are there any questions for Rick? John? What did this thing cost? Could you speak up, John? Vancouver to Goddard. How much does this mission cost?
The overall cost, including launch vehicle, is, I'm trying to remember now, it's under $250,000. It's like $240-something million, including the Minotaur 5.
Any other questions?
What's the mission goals and how long? What are the mission goals and how long will it last in orbit around the moon?
One of the key features of LADI was you fly the mission only as long as it takes to answer the questions, the scientific questions. And so the mission duration, I'll answer the second part first, is 100 days. 3 lunations, basically, in orbit around the moon as it goes through various environments. And the chief goals are to just characterize the spatial extent, the composition, and variability of the lunar exosphere. And the second thing is to establish once and for all whether or not there is this lofted, electrostatically lofted dust, and what the particle distribution is, how variable it is, where it occurs, and what are the underlying physics behind that. So it's a short duration mission. We have to do everything in 100 days. We take some time to get to the moon and commission the instruments, but when we hit the ground running, it's 100 days and the clock is ticking, and we do it on. Well, we'll hit the ground, yeah, after the 100 days. Very, very quickly.
Simone Dell'Agnello from INFN, Italy. In these 100 days, will you be able to do the laser communication experiment, which I understood takes an elliptic orbit?
I'm sorry, was that a question?
Yes, it's a question, yeah.
I'm sorry, I didn't understand your question.
In these 100 days of mission duration, will you be able to do also the laser communication experiment? Which,
no.
Okay.
The 100-day mission, there is no laser comm activity during that time. The laser comm activity is all during the commissioning phase after we go into lunar orbit, but before we actually drop down into a low altitude orbit. So the first about 60 days or so during commissioning, we'll be in a higher and much more stable orbit, and LaserCom will be doing its operations then.
We do have time for another question. I have one, Rick, on the...
Yvonne terrorized me into shortening this talk, so I'm up here trembling away.
Are the Minotaurs... available, or are they still making those?
Oh, that's a good question. Well, the Peacekeepers are all refurbished missiles that came out of silos and stuff. So Orbital has got the contract with the Air Force to refurbish these things and to offer launches on them. And so this is just the highest capability Peacekeeper-based system. So there's Minotaur 2s are actually based on Minutemen. And then you've got Minotaur 4, which is a 4-stage version of this, and Minotaur 5 is a 5-stage version of this. I don't know how many there are.
That's probably a secret, I guess.
I guess I wouldn't be able to tell you, I guess, if I knew it.